discuss a few areas here related to work and enthalpy that appear to be confusing. The first is the idea that work is minus integral pressure times delta V, or dV, where the pressure is the gas. So we have a piston and cylinder system, gas at pressure P. We have some external pressure. And for example, the gas expands because, say, we add heat and we get some work out of the system. Only time that we can write this down is when P equals that external pressure, which means the only time we can do it is when the system is reversible. So the pressure inside is exactly balanced. There's a differential difference in the pressure that allows the gas to push up against the external force. Otherwise, the work is going to be the external pressure, and indeed this means always that you can use the external pressure, minus sign here, to get the work. So the second example we'll look at is where an ideal gas is expanding. So I plotted pressure versus volume. So the pressure is changing, the gas and the volume is changing. The question is, how do we calculate the enthalpy change for an ideal gas? Can we write it as just the integral of Cp delta T, even though the pressure is not constant? So the pressure is clearly changing in this system. And the answer is yes. Important to remember, delta H, Cp delta T, always for an ideal gas. So even though we use this term Cp, this does not mean we're at constant pressure, right? So we can use Cp even though we're not at constant pressure. So the third example we'll look at is this idea that work is equal to delta H for an adiabatic reversible process, and that's equal to integral V dP, or if it's a liquid, volumes assume constant, pretty good approximation, V delta P. And this seems sometimes at odds with the fact that we write work as minus integral P dV. So where does this come from? Well, if we look at our general first law balance, and for reversible, we can make these two substitutions. And we look at our definition of enthalpy, then it's TdS minus PdV plus expanding out this term as PdV plus VdP. These two cancel. And so dH, which is the left side, is equal to TdS plus VdP. And adiabatic reversible makes this 0, since we say adiabatic and reversible. And then delta H is the integral of V dP. But remember, this is constrained to adiabatic reversible process.